Hello there, and welcome to the Last Signal channel. Tonight, we are looking at a universe that can still be seen long after it can no longer be reached. The night sky appears open, endless, and filled with places waiting somewhere beyond us. Yet distance alone is not the true barrier. Somewhere between what we can observe and what we can ever touch, the rules quietly change. Light may continue arriving from places that no future signal from Earth could ever enter. A galaxy can remain visible even after every possible route toward it has already disappeared. This means the universe shown by our telescopes is not the same universe available to our future. It is larger, older, and far less connected than it appears. And as cosmic time continues, even the evidence revealing that larger reality may slowly fade away. There may come an age when observers look into the darkness and find no trace that anything ever existed beyond their own galactic home. Tonight, we will explore what separates seeing from reaching, why most visible galaxies already lie outside our influence, and why humanity may live during a rare period when the wider cosmos can still be understood. Before we begin, subscribe to The Last Signal on YouTube for more calm documentaries about space, science, and the unanswered questions waiting beyond the familiar sky. The sky is not showing us the universe as it is. It is showing us a collection of moments that arrived late. In a deep field image, thousands of tiny galaxies appear suspended beside one another, each reduced to a faint point, or a soft smear of color. At first glance, they look like distant places sharing the same present moment with Earth, as though every one of them still exists exactly as the camera recorded it. That impression is natural, but it is wrong. Every object in the image has sent us information from a different time. Some signals began their trip comparatively recently, while others started moving toward us before Earth had formed. The photograph looks like one view, yet it contains many ages layered together. Sunlight reaches Earth after roughly 8 minutes, so even our own star is never seen in the exact present. Nearby stars impose longer gaps measured in years, and remote galaxies stretch that delay across millions or billions of years. The greater the separation, the older the message. By the time a signal reaches a telescope, the place that produced it may have changed completely. Stars may have been born and died, galactic systems may have merged, and vast clouds of gas may have collapsed into new generations of suns. The source may now look nothing like the faint image preserved in the arriving radiation. Several objects can therefore appear side by side while belonging to entirely different chapters of cosmic history. One may be shown after billions of years of development. Another may appear in a younger state, when its structure was still forming. A third may come from an age when the universe itself was close to its earliest visible form. The camera places them together, but time does not. Astronomy is therefore less like looking across open territory and more like receiving delayed records from separate eras. The detector gathers them in one moment only because their signals happen to reach us together. There are 3 different questions hidden inside the simple phrase, "How far away is it?" The first asks how long the arriving radiation has been in transit. The second asks where the source is now. The third asks whether anything sent from Earth today could ever reach it. Those questions can produce very different answers. A remote system may appear as it was billions of years ago, yet its present location can be much farther away because the space between us kept expanding during the trip. The image does not freeze the source in place. It records only the point from which the information began. While the signal crossed the cosmos, the geometry around it continued to change. This difference between travel time and present distance is where ordinary intuition begins to fail. In everyday life, a delayed letter may arrive after the sender is moved, but the movement is usually small compared with the distance involved. Across the universe, expansion can alter the separation so greatly that the source's current position no longer resembles the distance suggested by its visible age. The message arrives from where the object was, not from where it is now. Reachability adds another layer. Seeing a place does not prove that a route to it remains open. The radiation entering a telescope today may have left under conditions that no longer exist. During its flight, expansion can alter what later signals are able to do. A destination can remain visible because older information is still arriving, even after every new message sent from our region has lost the possibility of reaching it. That is the contradiction hidden inside the night sky. Observation feels immediate. Causality is not. Picture one faint point in a deep field image. Its glow may represent billions of stars in a structure so remote that the detected signal began moving long before humans existed. Photon by photon, that record crosses changing space and finally reaches an instrument near Earth. The detector measures its color, shape, motion, and chemical clues. Yet the present source may already lie beyond any future contact from here. The information can arrive after the possibility of reply has disappeared. This does not make astronomy futile. It makes astronomy more remarkable. Knowledge does not require physical arrival. A beam received across cosmic time can still reveal how matter gathered, how stars formed, and how the early cosmos evolved. We can learn from places no spacecraft will ever enter and read records written before our planet existed. What changes is the meaning of the image. It is not necessarily a map of destinations. It is a set of surviving traces. Some describe regions that remain within future influence. Others describe places whose later history has already separated from ours. All of them can appear equally clear on the same screen. That equality is visual, not physical. The sky gathers what can still be observed, not what can still be reached. Astronomy gives humanity access to a universe much larger than the region humanity could ever enter or affect. We receive evidence from beyond the limits of future action. The universe can remain visible long after contact has become impossible. The phrase edge of the universe creates the wrong picture before the explanation has even begun. It suggests one boundary placed somewhere in space, with everything on one side and nothing beyond it. Cosmology does not give us one such line. It gives us several different limits, and each answers a different question. Some concern how far information has traveled, while others concern the oldest available light, present recession, or future influence. The observable region is the part of the cosmos from which some influence has reached our location since the earliest stages of cosmic history. Its present radius is roughly 46 billion light-years, giving it a diameter of roughly 93 billion light-years. That size can sound impossible because the cosmos is a little under 14 billion years old. The apparent contradiction disappears once expansion is included. Light did not cross a fixed distance while the source waited in one place. The separation between source and observer kept increasing during the signal's flight. A region whose light traveled for almost the entire age of the cosmos can therefore be much farther away now than the travel time alone suggests. The first major limit is often called the particle horizon. It marks the greatest present distance from which any signal could have influenced us since the beginning, according to current cosmological understanding. This is not a physical object. It is the result of limited time combined with changing geometry. An observer elsewhere would have a particle horizon centered on that observer, not on Earth. Every observer has an observable sphere defined by the information that has managed to arrive there. Those spheres can overlap or include regions the other observer cannot yet see. That makes the observable cosmos less like one universal map and more like overlapping circles drawn from different positions. Another limit appears when telescopes look toward the oldest electromagnetic radiation that can travel freely to us. This glow is known as the cosmic microwave background. It was released hundreds of thousands of years after the beginning, when the early cosmos changed from an opaque plasma into a state through which light could finally move across great distances. Before that transition, charged particles scattered radiation so often that ordinary light could not travel far without being redirected. Then the expanding material cooled. Electrons joined with atomic nuclei. The constant scattering weakened, and photons began crossing space without immediately colliding again. Pause at that moment. The young cosmos did not suddenly become empty or calm. It remained hot, dense, and active. Yet light trapped in repeated collisions could finally continue onward. Those photons have crossed almost all of cosmic history before reaching instruments today. They form a glowing surface around every observer, but that surface is not a shell made of matter. It is the distance from which those early photons happen to be arriving now. An observer in another galaxy would see a different surface centered on that location. The surface of last scattering is therefore not the final border of existence. It is only the oldest electromagnetic view currently available. The total cosmos could extend far beyond it, either across a finite scale larger than we can measure, or without a global end. Current observations cannot settle that question, because regions outside our observable domain cannot send us evidence today. A third commonly discussed boundary is the Hubble radius. It is associated with the distance at which recession caused by expansion reaches the speed of light under a particular present-day description. This limit is useful, but it is not a permanent barrier to observation. Light emitted beyond it can sometimes still reach us, because expansion and geometry change during the photon's flight. Confusing the Hubble radius with a point of no return turns a useful measurement into a false boundary. The cosmic event horizon answers the harder question. It concerns not the oldest signal that can reach us now, but which events can ever send a signal that arrives here in the unlimited future. A galaxy can appear inside our telescopes, while its present activity already lies beyond that causal limit. Its older radiation can continue arriving even though a message emitted there now will never reach us. A signal sent from Earth today therefore cannot influence every galaxy whose earlier light remains detectable. These limits can be pictured as different rings on the same diagram. One marks past influence, another the oldest freely traveling light, a third a present recession threshold, and the last future causal connection. The rings are related because all arise from the history of expansion, yet exchanging one for another changes the entire meaning. The farthest thing we can observe is not automatically the farthest thing we can affect. The most important cosmic boundary lies much closer than the outer limit of sight. The expansion of the universe is not an explosion racing outward from one central point. It is a change in the large-scale distance between regions that are not held together by gravity. That distinction separates the real geometry of the cosmos from the picture most people instinctively carry. In an ordinary explosion, fragments move through an existing emptiness from a known center. This cosmic growth has no confirmed outside space, no universal middle, and no surrounding room into which galaxies are flying. From almost any widely separated galaxy, the broad pattern looks similar. Distant systems appear to recede, and the farther away they are, the greater that recession tends to be. This does not place Earth at a privileged center. It means the pattern belongs to the geometry itself. One useful comparison is a grid marked with evenly spaced points. Now let the spacing between every neighboring mark increase at the same time. No single point needs to be the center, and none of them must race across the grid. The measured separation grows because the scale connecting the points has changed. The comparison has limits, because a drawn grid expands inside a larger surface, while the cosmos does not require an external room. Still, it captures the key relationship. More intervening space means more accumulated increase in distance. A faraway galaxy has an enormous interval between us, so countless small increases add together across the full span. That is why recession grows with distance. Gravity interrupts this pattern on smaller scales. The solar system does not expand with the cosmos because the sun's gravity keeps its members bound. The Milky Way does not swell in the same way either, because its stars, gas, and dark matter belong to one gravitational structure. Even tightly connected groups of galaxies can resist the general growth of separation. Large-scale separation becomes dominant between regions that are too far apart to remain bound as one system. This is why the phrase "everything is expanding" is misleading. Atoms are not stretching. Human bodies are not growing with the cosmos. A measuring ruler does not lengthen alongside the distance it is meant to measure. The effect appears across immense unbound intervals, where local forces no longer control the relationship. The strangest consequence emerges when recession exceeds the speed of light. At first, that seems to violate relativity. General relativity states that no object moving locally through space can overtake light in its immediate surroundings. A spacecraft beside a beam cannot accelerate past it. A particle cannot cross its neighboring region faster than light does. Recession across extreme distances is different because it is not one object locally breaking the limit. The total distance between extremely separated regions can grow faster than light, as the geometry changes across the entire interval. No nearby observer watches a galaxy shoot past a local light beam. The result appears only when growth is added across a vast separation. Consider a photon traveling through such an interval. Locally, it always moves at light speed. It never becomes tired, slows down, or loses a race against a neighboring object. Yet the distance remaining ahead of it can evolve while it travels. Behind it, crossed regions continue changing. Ahead of it, new separation may accumulate between its position and the destination. The photon's motion remains lawful at every point, even while the larger route becomes harder to complete. This is not a loophole in relativity. It is one of the results relativity allows when space-time itself is dynamic. Traveling light carries a record of that large-scale change. As the geometry changes, the wavelength of the radiation becomes stretched. Visible light can shift toward redder wavelengths, while other radiation is drawn farther into the infrared or radio range. This cosmological redshift is not merely the ordinary effect of an object moving through fixed space. It also preserves information about how the interval expanded while the signal crossed it. By measuring stretched wavelengths across many galaxies, astronomers can reconstruct the broad history of cosmic growth. That history is well established, even though one important detail remains unsettled. Different measurement methods do not agree perfectly on the exact present expansion rate. Observations based on the nearby cosmos produce one value, while measurements tied to the early cosmos produce another. The disagreement may point to systematic errors, incomplete measurements, or physics not yet included in the standard model. What it does not show is that cosmic growth itself is doubtful. Multiple independent observations confirm that distant, unbound regions are separating over time. Toward the end of the 20th century, another discovery made the long-term picture more severe. Measurements of far-off stellar explosions showed that the large-scale separation was not gradually slowing under gravity, as many researchers expected. It was accelerating. The cause remains unknown. Dark energy is the name given to the component or property associated with that acceleration, not a complete physical explanation. The label describes the effect more confidently than the underlying mechanism. If the acceleration continues in approximately its present form, future light paths change. Connections that seem possible on a frozen diagram can fail in an evolving cosmos. A static map may show two galaxies separated by a finite line. The real universe adds time, changing geometry, and a route whose length does not remain fixed while the traveler moves. Once those ingredients are included, some paths never close the gap. The accelerating geometry does not merely place destinations farther away. It can remove arrival from their future. One light pulse leaves Earth and begins moving toward a galaxy far beyond the Milky Way. In its immediate surroundings, nothing unusual happens. The pulse travels at the speed of light, exactly as relativity requires. It does not slow because the destination is remote, and it does not lose energy because the route is difficult. At every local point, its motion remains ordinary. The problem lies in the geometry through which it must travel. Arrival depends on more than speed. It depends on whether the pulse's path and the galaxy's later history can ever meet. The cosmic event horizon marks the boundary between events that can still send us information and events whose newly emitted signals will never arrive here, assuming accelerated expansion continues in its present form. Viewed from Earth today, that horizon is often placed at roughly 16 billion light-years in a commonly used present distance description. The exact value changes slightly with the cosmological model and the definition of distance being used. The principle is more important than the figure. Beyond this causal boundary, waiting longer does not solve the problem. The signal can continue moving correctly through every nearby region, while the total separation evolves in a way that prevents contact. This can sound as though light is being pushed backward. It is not. A photon always advances locally in the direction it was sent. Yet progress toward a target is measured across the whole changing route, not only across the photon's immediate neighborhood. If the interval ahead grows quickly enough, the remaining distance does not have to fall to zero. The beam keeps moving, but no arrival event appears. That is the meaning of a causal horizon. It does not describe a wall the pulse strikes. It describes the absence of a shared point ahead. This also explains why a galaxy can recede faster than light, and still remain visible. The light entering our instruments today may have left when the relevant conditions were very different. Early in its flight, the photon may have moved through regions where the pattern of expansion allowed it to make effective progress toward us. Only later did accelerated growth reshape the connection between the source and Earth. The old signal can therefore arrive even when a new one emitted from the same galaxy would fail. Visibility and future communication are separated by cosmic history. The Hubble radius must not be confused with this event horizon. The Hubble radius identifies a present recession threshold associated with the speed of light under a particular description. A photon can cross that threshold and still reach an observer if the expansion rate and surrounding geometry change favorably during its trip. The event horizon is stricter. It asks whether any signal beginning at a particular event can ever enter the observer's causal domain, no matter how much time passes. A useful way to picture this is through light cones. Each event has a set of possible locations that light or any slower influence can reach. For contact to occur, the light cone of the signal and the later course of the target must intersect. Outside the causal boundary, those paths remain separate. The geometry does not deny motion. It denies meeting. Extreme spacecraft speed cannot change that structure. A traveler moving close to light speed can experience far less elapsed time than observers who remain behind. This effect, known as time dilation, could make certain enormous journeys feel shorter to those aboard the craft. It does not open destinations that lie outside every possible light path from the departure point. The travelers may reduce their own experience duration, but they cannot create a causal intersection where none exists. Relativity changes the clock. It does not redraw the reachable region. Ideas such as wormholes and warp geometries are often raised as possible escapes. Physics can describe mathematical spacetimes containing shortcuts or unusual distortions. Some solutions suggest that two remote regions could be connected by a path far shorter than the direct distance between them. Others describe a moving distortion in which the craft stays locally below light speed while the geometry around it changes. These ideas remain speculative. No experiment has demonstrated a stable, traversable wormhole, and no engineering method is known for creating the required geometry. Many proposed models also depend on forms of negative energy or matter configurations that have not been shown to exist in usable quantities. That does not justify declaring every future discovery impossible. It does mean that established physics offers no demonstrated mechanism for crossing a cosmic event horizon. Now, hold the image of the original pulse. It continues outward through an expanding cosmos. In every small region, it behaves exactly as light should. It crosses one interval, then another, while the chosen galaxy follows its own course. The pulse does not stop. It does not turn around. No obstruction blocks it. Still, the two histories fail to meet. The signal stays real, its motion stays lawful, and its destination is absent from what lies ahead. This is more severe than an extremely long travel time. A long trip has an arrival placed far ahead. Causal unreachability has no arrival at all. Return to the deep field image, but do not read it as a catalog of future destinations. Read it as a field of old arrivals. Each faint point still sends information into our instruments, yet most of those sources no longer belong to the region our actions can ever influence. Under the standard cosmological model, a widely cited estimate places roughly 94% of the galaxies we can currently observe beyond our future causal reach, more than 9 out of 10. That number sounds like a claim that the visible cosmos has somehow disappeared. It is not. The systems remain part of physical reality, and many may continue evolving for immense spans of time. What has been lost is not existence. It is the possibility of beginning a connection from here now. The estimate depends on how the cosmos is modeled, how distances are defined, and how the galactic population is counted. It should not be treated as an exact census carried to the final object. Small changes in cosmological assumptions can shift the percentage. Yet the broader conclusion remains firm within current understanding. The observable region is far larger than the part of it that can still receive a signal launched from our surroundings today. Choose one unnamed point, buried among thousands in the image. The radiation entering the detector may have begun its course when that system was much closer in the relevant cosmological sense. During the billions of years that followed, the interval between its region and ours continued to grow. The photons kept coming. The source did not remain where the picture seems to place it. Its present distance became much greater, and its future path separated from every new message that could begin here now. The visible image, the age of the arriving radiation, the source's current position, and its reachability are four different facts. A telescope gives direct access to the first and helps infer the others. It does not collapse them into one shared present. This produces a strange asymmetry. We can receive a record from a place that cannot receive a reply. The incoming radiation may reveal the motion of stars, the distribution of matter, the chemistry of gas, or the growth of a young galactic structure. With enough observations, researchers can reconstruct conditions that existed before Earth formed. The information is rich enough to support real science. The relationship is still one way. Imagine the record arriving photon by photon across an expanding geometry. Each detection adds another fragment to an ancient account. A trace of hydrogen appears in the spectrum. A distorted shape hints at an interaction with a neighboring system. A shift in wavelength records motion and cosmic expansion. The image gradually becomes more informative, even while the possibility of sending anything back becomes more remote. There is no moment when the source announces that contact has closed. No dark line sweeps across the detector. No warning appears beside the data. The final separation is written into the future paths themselves. By the time observers understand what they are seeing, the opportunity for a new signal to arrive there may already be absent. This does not diminish astronomy. Physical access is not the only form of knowledge. Scientists study the interior of stars they will never enter, the earliest visible radiation they cannot revisit, and environments no probe could survive. Observation allows matter in one region to learn about matter in another without crossing the full distance. An unreachable source can still answer questions through the evidence it emitted long ago. What astronomy cannot do is turn received information into mutual influence. A sharp image does not create a route. A detailed spectrum does not restore a common future. The distinction matters because the word observable often sounds broader than it is. It tells us that some signal has reached us. It does not promise that a signal starting now can travel the other way. In a static cosmos, seeing and reaching might feel like different versions of the same problem, separated mainly by technology and patience. In an accelerating cosmos, they become fundamentally different categories. One concerns evidence from the past. The other concerns possible events ahead. The 94% estimate places that difference on an almost unimaginable scale. Most of the visible population belongs to the first category alone. Their light remains available to study, but their later history is no longer open to intervention from our region. Even a civilization with perfect telescopes, vast energy, and unlimited determination could not convert those old arrivals into a conversation under known physics. The obstacle is not weak propulsion. It is not the fragility of biology or the shortness of a human life. It is the absence of a causal path. Looking at a clear sky can therefore create two opposite impressions at once. It appears crowded with places. It is dominated by separation. The points remain visible, structured, and measurable, while the future connection between their regions and ours has already failed to form. The sky looks open because light still arrives. Causality says otherwise. The map of future contact is not fixed. It changes as the universe changes. A galaxy can remain visible, while the route that would connect it to us disappears from every possible future. That does not mean the galaxy suddenly vanishes from the sky. Its older light can continue arriving for an immense span of time. The change begins in causality long before it becomes obvious in observation. In an accelerating cosmos, the set of unbound regions that can still exchange newly sent signals becomes more restricted. The objects remain where their own histories place them, yet fewer future light paths can cross the growing distance between their regions and ours. Think of a communication map rather than a physical chart. The points representing galaxies may stay in place on the page. The lines between them are what fade. One by one, routes that once belonged to the future no longer connect. Nothing dramatic announces the change. No flash crosses the heavens, and no border becomes visible through a telescope. The geometry simply stops, allowing a newly emitted signal to arrive. Observation responds more slowly. Older radiation already on its way can continue to reach us after the source has passed beyond future influence. As expansion stretches that radiation, its wavelength grows longer. Visible light shifts toward the infrared. Infrared radiation is drawn toward radio wavelengths. The received energy weakens, and each new event at the source appears to unfold more slowly from our perspective. Over vast ages, the system becomes harder to detect. Its light does not switch off at one precise moment. It thins, reddens, and recedes toward the limits of measurement. Imagine an observatory returning to the same remote source after intervals longer than entire civilizations. At first, the galaxy still looks familiar, though slightly fainter. Much later, its spectrum has shifted so far that different instruments are needed. After further cosmic ages, only the most sensitive detectors can separate its signal from the surrounding noise. Nearby stars continue shining across the local sky, while the remote source becomes a weaker trace of a larger cosmos that is no longer open to contact. The process is slow enough to escape every human lifetime. No one alive today will watch a distant galaxy cross from clear visibility into final darkness. The relevant changes unfold across billions and tens of billions of years. This is not an approaching catastrophe. It is the long-term behavior of an expanding geometry. The same future affects the oldest, widespread light we can observe. The cosmic microwave background now fills the sky as a faint remnant of the early universe. As expansion continues, its wavelengths are stretched farther. Its temperature falls, and its signal moves into ranges that become increasingly difficult to detect. Future instruments may be extraordinarily advanced, yet technology cannot recover radiation that has been stretched beyond practical measurement. The evidence does not become false, it becomes unavailable. That difference matters. A scientific fact can remain real even after the signals needed to discover it have faded from reach. External galaxies currently allow astronomers to measure large-scale recession. The ancient microwave glow gives access to conditions from the young cosmos. Patterns in matter reveal how structure developed over time. Together, these records allow observers to reconstruct a history far larger than their own region. The present era contains all of them at once. That combination may not last. In the far future, external systems can become too dim and redshifted to study. The early background radiation can fall below detectability. Only the gravitationally bound surroundings may remain clear. A future observer could possess better mathematics, sharper instruments, and deeper knowledge of local physics while having fewer clues about the wider cosmos than we have now. The limitation would not come from ignorance. It would come from missing evidence. This future is conditional rather than absolute. It assumes that dark energy continues behaving approximately as current observations indicate. If its properties change in a fundamental way, the long-term geometry could develop differently. Current measurements, however, favor continued accelerated expansion. Under that picture, the communication map keeps contracting while the visual record fades behind it. What can be known depends partly on intelligence and technology. It also depends on whether the universe still delivers the information. Scientific discovery, therefore, has a cosmic window. Some truths are available because their evidence is arriving now. Later observers may inherit the same physical history, but not the same access to it. What gravity keeps begins with a correction that brings the scale of the problem closer to home. Cosmic expansion does not stretch planets away from their stars or pull neighboring stars out of a galaxy. On local scales, gravity and other binding forces are far stronger than the gradual large-scale increase in distance. Earth remains attached to the Sun, and the solar system continues moving as one gravitational structure. The Milky Way also holds together. Its stars, gas clouds, stellar remnants, and dark matter remain connected by their combined attraction rather than following the general expansion between unbound regions. The same principle extends beyond our galaxy. The Milky Way belongs to a collection of several dozen galaxies known as the Local Group. This group includes many small systems, along with its two dominant members, the Milky Way and Andromeda. Their mutual gravity is strong enough to overcome the expansion acting across the space between them. Andromeda is therefore not being carried permanently away from us. It is approaching. Several billion years from now, the two great spiral galaxies are expected to pass through one another and begin a long gravitational interaction. The word collision can make the event sound far more violent at the stellar level than it will probably be. Galaxies contain hundreds of billions of stars, yet those stars are separated by enormous intervals. Even when two galactic structures overlap, individual stars have so much empty space around them that direct impacts remain unlikely. The major changes happen through gravity. Orbits are disturbed, streams of stars are drawn outward, gas clouds are compressed, and the shapes of both galaxies are gradually transformed. Some regions may experience increased star formation as clouds of material are forced together. Other stars may be thrown into wider paths around the combined system. The central black holes are expected to move toward one another over deep time, and may eventually merge as well. The exact details depend on the galaxy's future motion, their internal structure, and the distribution of unseen matter around them. The broad result, however, is strongly expected. Two recognizable spirals will become one larger and more rounded galactic remnant. Consider how the sky could change during that encounter. Andromeda already appears as a faint patch under dark viewing conditions, though only its bright central region is easily visible without instruments. Across immense periods, it would grow wider and brighter. Its stars would spread across a greater portion of the sky, while long streams of light trace the gravitational distortion of both systems. The familiar band of the Milky Way would no longer remain the only great galactic structure overhead. For observers living somewhere in that distant era, the heavens could be filled with overlapping arcs, compressed clouds, and newly forming stars. The transformation would not happen in one night. No single generation would witness the whole event. Each age would inherit a sky only slightly different from the one before it, while the full change unfolded across periods too long for any ordinary memory. Eventually, repeated passages would slow the relative motion. Gravity would redistribute energy throughout the system until the separate galaxies lost their original forms. Smaller members of the local group would also remain nearby, though many could later be absorbed into the growing remnant. What survives is not a frozen copy of the present. It is a connected region that continues changing while remaining gravitationally bound. Beyond it, the wider pattern is very different. Galaxies that do not belong to the local group lack a sufficiently strong mutual connection with us. As accelerated expansion continues, those external systems recede farther, and their incoming radiation becomes progressively harder to detect. They do not take the local group with them, nor does expansion tear the merged remnant apart. Local gravity preserves the structure even as the distance to unbound regions grows beyond future contact. This creates a sharp contrast between what telescopes reveal today and what remains permanently connected over cosmic time. The visible cosmos contains countless galactic systems spread across an extraordinary volume. The region that stays in our causal company is much smaller. Its long-term boundary is defined less by what can currently be photographed than by what gravity has already tied together. That surviving domain may eventually contain one dominant galaxy, its surrounding stars, smaller companions, wandering planets, and the remnants of earlier systems. It will still be vast by any human measure. Compared with the universe now visible, it will be a narrow inheritance. This outcome should not be understood as a loss approaching human civilization. The merger itself lies several billion years ahead, and the disappearance of external galaxies from practical observation takes far longer. No present society is watching its surroundings collapse. This is the architecture available to any remote descendants or other intelligence that might inhabit our region in the far cosmic future. They may possess access to more stars than humanity could ever visit. They may cross parts of the merged system and study worlds formed long after the present sun is gone. Yet nearly all the galactic structures now visible through powerful instruments will no longer belong to the region they can observe or influence. Gravity preserves a home region. It does not preserve the wider cosmos. Imagine another observer standing beneath a sky that feels just as central as ours. Their planet circles a distant star, their instruments scan outward, and every direction appears to place them at the middle of what can be seen. They are not located at a privileged cosmic center. neither are we. Every observer occupies the center of an observable region defined by the signals that have managed to arrive there. The same is true for the smaller domain that remains open to future influence. From that distant world, Earth may lie somewhere inside the visible record, outside it entirely, or beyond any possible future exchange. The number of possible worlds is enormous. Planets appear to be common around stars, and many systems contain bodies at distances where liquid water could exist under the right conditions. That abundance makes multiple origins of life plausible. It does not make them certain. Life may begin easily, or it may require a chain of rare events that seldom repeats. Intelligence introduces another uncertainty. A living world does not automatically produce technology, radio signals, or a society capable of studying the stars. No confirmed extraterrestrial life or artificial signal has yet been detected. That fact should remain separate from every estimate about how many inhabited worlds might exist. Large numbers create opportunity. They do not create proof. Cosmic horizons add a limit that does not depend on biology at all. If two civilizations lie beyond one another's event horizons, no message sent after that separation can complete the trip. A stronger transmitter cannot fix the problem. A longer-lived society cannot wait its way through it. The barrier is not weak equipment or insufficient patience, but the absence of a causal connection between their future events. Both societies could continue to exist. Both could develop extraordinary science. Neither could begin a conversation with the other. Older information might still cross the divide. One civilization could receive light emitted by the other's galaxy under earlier conditions. By the time those clues arrive, however, any reply beginning now may have no destination it can ever reach. This creates a form of silence that requires no decision. No one has to hide. No society has to refuse contact. No unfamiliar communication method needs to be blamed. The separation follows from geometry alone. Now, picture two inhabited worlds in different galactic systems. Each receives an old record from the other's region. One sees the light of stars that have already changed. The other measures traces produced before either civilization reached its present form. For a moment, each may learn that company once existed somewhere beyond its own sky. Still, no future exchange follows. Their timelines contain evidence of one another without containing a shared conversation. That possibility is emotionally powerful, but it must not be confused with an observation. We do not know whether either world exists. We know only that if civilizations occupy causally disconnected regions, standard physics prevents newly sent messages from joining their futures. This does not solve the silence closer to home. The Milky Way remains small enough for light to cross on timescales that are long but physically possible. A signal from one side of the galaxy could, in principle, reach the other. That makes the absence of confirmed contact within our own galactic region a different problem. Cosmic acceleration cannot explain every local silence. Life may be uncommon. Technological societies may remain detectable for only a brief period. They may communicate through methods we do not recognize. Our own searches have covered only a small fraction of the possible sky and signal types. None of these possibilities has enough evidence to stand as the answer. They describe open paths of investigation, not conclusions. It is also possible that many worlds contain simple life, while almost none develop long-lasting intelligence. Distance is only one filter. timing may be just as severe. Two civilizations can inhabit the same galaxy and still miss each other by millions of years. The first may vanish before the second begins listening. Unlike separation beyond an event horizon, these local obstacles are matters of probability, duration, and detection. They remain uncertain. The distinction is essential. Some silence comes from an absolute causal limit under the standard cosmological model. Other silence exists inside regions where contact is physically allowed but has not been observed. Combining those situations creates false certainty in both directions. The size of the visible cosmos does not guarantee intelligent company. The absence of a detected message does not prove that Earth is alone. What can be said is narrower and more precise. Reality may contain life beyond our region. Some of it, if it exists, may be forever excluded from communication with us. The question of company can remain open even where the possibility of contact has already closed. In the far cosmic future, an observatory turns its instruments beyond the merged galactic remnant that once contained the Milky Way and Andromeda. Its technology may be more advanced than anything imaginable today. Its detectors may be colder, larger, and more precise. Yet the sky outside the local stars appears almost empty. No neighboring galactic systems mark the darkness. No broad population of remote galaxies provides a pattern of recession. The instruments search farther, but there are no external reference points left within practical detection. This is not a failure of intelligence. It is a shortage of arriving information. By then, unbound galaxies will have receded so far that their light has been stretched beyond useful observation. The cosmic microwave background will also have faded into wavelengths so long and weak that even exceptional instruments may not recover it. The history remains real. The evidence does not. Future astronomers would still understand gravity, nuclear physics, stellar evolution, and the motion of objects within their own galactic system. They could map stars with extraordinary accuracy and study black holes, planets, gas clouds, and stellar remnants. Their local science might be deeper than ours in every measurable way. When they ask how large the cosmos is, however, the surviving observations could point toward a radically smaller answer. Without visible galaxies beyond the local remnant, there would be no obvious large-scale pattern showing that distant systems recede from one another. Without that pattern, the expansion of the universe might not appear as an empirical feature of reality. The concept could still arise mathematically, but mathematics alone would not prove that the surrounding cosmos once followed such a history. Without the ancient microwave glow, another major record would be missing. That radiation currently preserves information from a time when matter and light were emerging from the dense early universe. Its small variations allow modern cosmologists to test models of cosmic age, composition, geometry, and structure formation. In the remote future, those clues may no longer enter any detector. Primordial chemical abundances could also become harder to interpret after countless generations of stars have altered and recycled the available matter. The old signatures would be mixed with the products of stellar interiors, explosions, and galactic evolution. One category of evidence would disappear after another. Picture the observatory continuing its survey. A telescope sweeps across every direction beyond the local stars. The instruments collect silence where external galaxies once filled the sky. Researchers improve the detectors, reduce the noise, and repeat the measurement. The result remains the same. The absence is not caused by poor equipment. nothing brighter is still arriving. From the evidence available, those astronomers could reasonably conclude that their own galactic system forms nearly the entire measurable cosmos. They might describe it as an isolated structure surrounded by darkness without detectable beginning or larger environment. That conclusion would be incomplete, but it would not be foolish. It would fit the facts they could test. Science cannot use evidence that no longer reaches the observer. This creates an unsettling limit on knowledge. A civilization can improve its reasoning while losing access to the conditions needed for a wider explanation. Truth does not change, yet the path to discovering it can close. Modern observers occupy a different position. We can compare nearby galaxies with systems seen at much earlier stages of development. We can measure redshift across enormous ranges of distance. We can detect the ancient background radiation and study the chemical remains of the young cosmos. None of this means current cosmology is complete. Dark energy remains poorly understood. The exact expansion rate is still debated, and the full extent of the universe remains beyond direct measurement. What matters is that several independent lines of evidence are still available at the same time. They allow one observation to test another. A future civilization may inherit greater intelligence and poorer access. Its best theory could be elegant, internally consistent, and limited by a sky that has stopped revealing the larger history. This scenario depends on accelerated expansion continuing in approximately the manner suggested by current measurements. If dark energy changes its behavior over deep time, the future may develop differently. Under the standard picture, however, the disappearance of evidence is not a technological problem waiting for a better instrument. It is a consequence of the signals no longer arriving. The most disturbing part is not that distant objects become difficult to see. It is that an entire account of cosmic origins can become impossible to reconstruct from one region. The universe can erase the evidence of its own history without erasing the history itself. The brief age in which the universe can be read is visible inside a single deep field image. What first appeared to be a chart of faraway destinations now carries a different meaning. Each point is information that happened to arrive while the wider cosmos was still available to observation. Some of those sources remain open to future influence. Many do not. Their light still enters our instruments because it began crossing space under conditions that belong to an earlier universe. The image is therefore not a promise of future travel. It is a readable record of places whose later histories may never intersect with ours. The present era occupies only a narrow interval within the full life of the cosmos. Galaxies beyond our bound region are still visible. The large-scale expansion can still be measured. The ancient microwave glow still reaches detectors. Stars continue forming inside clouds of gas, and enough separate clues remain to reconstruct events that happened before Earth existed. None of this will remain equally accessible forever. In the far future, star formation is expected to decline as usable gas becomes harder to gather into new stellar systems. Existing stars will continue through their life cycles, leaving behind white dwarfs, neutron stars, and black holes. Across vastly longer spans, even the familiar era of shining stars will pass. The cosmos will not end at that moment. It will continue into conditions colder, darker, and less active than anything visible today. The duration of that future may exceed the present star-filled age by an almost incomprehensible margin. Against that scale, the current observational window is brief. Our location is not special in space. Earth does not occupy the center of existence, and no physical law points toward this planet as a chosen destination. Our timing, however, allows several ancient records to remain available together. Light from remote galaxies reveals structures formed during different phases of cosmic history. The background glow carries traces from the young universe. The movement and chemistry of matter provide additional ways to test the same broad account. These records were not prepared for human observers. They were not sent with intention. They simply continued through space until a small world developed instruments capable of receiving them. Observation cannot reverse expansion. It cannot restore contact with a region that lies beyond future causal reach. It cannot transform an ancient image into a destination available to travelers. What it can do is recover real knowledge from information that has crossed distances no spacecraft will ever complete. Light carries more than brightness. Its wavelength can reveal motion. Its spectrum can expose chemical elements. Its shape can show gravitational distortion, galactic interaction, and the distribution of matter. Its travel time allows observers to compare different periods of cosmic development without leaving their own region. Astronomy turns delayed radiation into a physical history. That achievement does not depend on possessing the places being studied. It depends on reading the signals accurately while they remain available. Consider one ancient photon entering a detector. It may have left its source before the sun formed. During its passage, stars were born, planets gathered from disks of dust, and life appeared on at least one world. The interval it crossed continued expanding around it. Its wavelength stretched, and the galaxy that released it moved into a future increasingly separated from ours. The photon still arrived. It struck an instrument, produced a measurable event, and became one small part of a larger understanding. Nothing about that moment creates a reply. The distant source does not know that its radiation was received. No message sent back today may ever reach the place from which it came. Still, the arrival matters. Matter in one corner of the cosmos has preserved information about matter in another. On Earth, that information can be collected, compared, questioned, and understood. For a limited time, observers can look beyond their gravitational home and reconstruct a domain much larger than anything they can enter. There is no need to call this destiny. The significance comes from the physical fact itself. A universe governed by impersonal laws produced light, structure, memory, and eventually minds capable of reading the patterns. Those minds appeared while the records were still arriving. Later observers may inherit a darker view. Earlier observers would have lacked the stars, heavy elements, and stable worlds required for complex instruments. The readable era exists between those extremes. It follows the first long development of structure and precedes the disappearance of most external reference points. We happen to live inside it. The deep field image now becomes something quieter than a map and more valuable than a collection of unreachable targets. It is a temporary record still open to interpretation. Each tiny source represents a physical history carried across changing geometry. Some records arrive from regions that remain causally connected. Others come from places already beyond reply. The distinction is invisible in the photograph. It emerges only when expansion, time, and future causality are understood together. Eventually, the larger cosmos may disappear from every instrument inside our bound region. The histories recorded in those distant systems will continue, but their light will no longer contribute to knowledge here. For now, the detectors remain open. Ancient photons are still arriving. The wider universe can still be read, even where it can never be reached.